Well, good evening, everyone. I hope everybody has had a good time. And give me a green circle if you can hear me. Okay, Matthew, are you there? Okay. Okay, what you need to do is you need to send me your homework. I want you to put in the text part of the message, put it works if it works. And if it doesn't work, put, tell me it doesn't work. And if you have any reason why it doesn't work, you can explain yourself a little bit. If it works 100%, they'll put it works. Those will be the ones we specifically grade. So go ahead and take a couple seconds to send that because once I start explaining how it works, and you can't turn it in after that or you'd be copying my work. When you get that sent to me, please give me a green circle. You won't get any reply back on this one, so make sure you are sending it to the right place. Dante, you have a question?
Yeah, are we sending the? We're not sending the .asm folder, are we? No.
No, send me the .asm
The
file.
.asm. Oh, okay.
Yeah, and also a note inside the message that tells me whether it works or not.
Okay. Thank you.
Anybody still trying to send one? Mikkel, you have a question?
No, I was raising my hand to say I'm still sending it.
Okay. I'll give you another 30 seconds. After that, it's going to be late if you send it to me.
When I try to test the thing out, it just says file not found. So could I just send a text file?
Yeah. Okay, let us get started here. I assume everybody saw the announcement that we have an exam coming up a couple classes from now. Tonight, we're going to finish up the SAP2. Well, not finish it up, but we'll get a lot more accomplished. On Wednesday night this week, we will start to talk about the SAP3 as well as the 8085. And then next Monday, we'll be looking at the Intel 8086 and 8088 instruction set. And then on Wednesday next week, which is the 17th of November, we'll be having an exam over all the material we've covered since the last exam. Plus, remember, we omitted some material right at the end of the last session for that test. So the VHDL, things having to do with any of the hardware description languages or any programmable logic devices, maybe even memory, some of those things that were that same bus architecture, some of the things that were just at the trailing end of the first session. Additionally, you'll have to know things from the beginning of the class because everything builds on everything here. So it's not compartmentalized in that you could just study this stuff and be good enough. You have to make sure that you still remember all the things we had done prior to that. Does anybody have any questions about the exam? Dante?
Are you planning to host another review session before the exam?
I don't think I will. I think we'll probably have a little bit of time at the end of the next two classes where we can do a little review there.
Okay.
Anybody else have any questions? Now, the grade on this next exam, plus the very original exam, if we were to look at the syllabus, they fall in this category of exams here, which is 20% of your grade. The final exam doesn't count as part of that. So I can't really tell you anything about the grade you have so far until I see the grade you get on the next one, because those two taken together give you this whole 20%. And a lot depends on what's on your exam. Not everybody gets the same exam. I'm going to look at your homework. If you're either not doing the homework or you have you're not really demonstrated for the next home. We're going to have another homework between tonight and Wednesday. If you're not demonstrating that you're actually taking it seriously, there'll be some questions on the exam that wouldn't have been there otherwise. So you want to make sure when you do these programming assignments, you try to get them right. Remember, in assembly, like most languages, it's either right or it's not right. It's a binary thing. It's not almost correct. So, you know, you want to make sure you try hard, block off some time to work on it. These classes are intentionally a little bit shorter than they would be if we had a full lab, so that you have time to spend homework on these things. And I did talk to a few of you this week, and you were doing the ones I talked to were doing very well on the homework assignment. So, you know, don't blow this off. This is very important stuff as far as getting you, you know, into the mindset for the last portion of the course, as well as giving you a skill that you wouldn't have otherwise. Okay. Yeah, you have a question, Robert?
Yeah, are we gonna go over how you would have done this?
We're actually going to do that right now. I was waiting for everybody to get theirs turned in, because I tend to find if I don't, what happens, somebody will turn theirs in. They'll show up late to class. They'll turn theirs in, and theirs will look an awful lot like mine. And, you know, I want to see what you did, not what I did. I know what I did. So yes, we're going to cover a little bit of how to do it. Now, the way I did it is not the way I would do it if I were consulting for somebody and they needed the fastest possible, smallest possible code. Instead, I wrote it in the way a student at this point should be writing the code. Remember, with assembly language, unless you're on a machine like a microcontroller that does not have good C support, you probably shouldn't be writing directly in assembly language unless that's the only language the device supports. You would use assembly language as an optimization tool under very, very specific cases, but knowing how it works will make the other languages more understandable to you. You'll program much, much better in C or Java or some of the others by understanding how it works at the assembly language. But I almost guarantee you that the assembler, which is what you call a compiler in assembly language, that the assembler generates better assembly language than most of us can write. And so when we write something at a high level language, and we saw kind of in some of the examples we were doing how it might algorithmically do that, it could probably turn out some better assembly than we could unless we had a very, very specific performance problem or we were fixing a bug in the firmware. Both of which, for instance, the assembler wouldn't know about the bug. And also, if we get to the point where we care about that type of performance, most of us are probably not the person they should be calling to have that fix done. There probably are others who could handle that task a little more, but we still nevertheless need to know how to do it. So what I want to do is go over a possible way to do it. Now you might go, oh, I almost did that. That's kind of like what I was doing. Well, maybe. That's also, or ask yourself, did it work at the end? And just kind of formulating a plan doesn't completely solve the problem each time. So let me put these two pieces of paper out of the way here so I don't keep picking them up and reading them again. And I think I called mine, let me look here. Yeah, I called it HWK1. So let's kind of take a game plan, look at this. Our goal was to take some number and make a copy of it into another place. Nowhere were we told we had to save the first number. We could if we wanted to, but it was not part of the specification. And write it or have it be reversed. So a bitwise reversal of an 8-bit number. And to do that, we look at our instruction set and we look specifically for instructions which might be helpful in causing that to occur. Now, one of the things we see at first is this doesn't look computable, meaning there's not some short arithmetic problem you can solve and get it to work. So that is one of the big problems I find with people that program initially in a new language. Is the first thing some people do is when they have a problem like this, they go online and they look to see if there's a solution somewhere. Well, that's not the way you learn to program well. You tackle the problem and you see how you did, and maybe afterwards you compare it against other people's solutions. But you don't go to some place like Stack Overflow and look to see. I know a lot of people that do that, and they're terrible programmers. Some of them make a living at it, but not the living they could be making. Treat this like a puzzle. How are you going to solve it? How are you going to make it happen? One of the possible solutions to this could have been there's a simple computation you could do that gives you the answer. Well, it turns out there isn't. But we do have to at least think about that problem as being something that could have happened. What it would mean would be that if I took 8 of those and I turned them into those, is there some math I could perform that would give me the same solution as that? So is there some math I could perform against this number that would yield this number, which is the same math that if I performed it against 0, I would get this. And if I performed it against this, I would get that. So that would be something to look at and to think about for a few minutes and work some little problems to see if it happened. In this case, probably not anything useful pops up, at least nothing we could use the instructions that we have to operate. Remember, we don't have multiplication and division except by 2's. So we can multiply or divide by 2, but remember last time I showed you an example where you got to paste them down. I hope some of you followed up on that example to see what you do with fixed point binary so that you would be able to handle the arithmetic necessary, for instance, to find an average of numbers which are divisible by some power of 2. Well, here's the thing we need to observe by this. First of all, bit 7 goes to bit 0, bit 6 goes to bit 1, bit 5 goes to bit 2, bit 4 goes to bit 3, and so forth. So what we need to do somehow is capture the fact that this bit is on and then turn that bit on as a result of it. Now, if you notice the difference between these are increasingly becoming smaller. 7 to 0 is 7, 6 to 1 is 5, 5 to this is 3, this is 1. So we would think, is there some arithmetic we could do? Well, another way to look at it would be, if it were possible to make this number be directly underneath that number, I could simply pass the number straight down into that position. So I would ask myself, is it possible to somehow rotate the numbers so that could happen? We have a rotate instruction. So for example, if we took this number, which initially is all zeros, and we were to rotate it so that this position fell underneath that position, then we just simply duplicated that number below. Well, how do we duplicate a number and not affect any other number in any other position? We'd ask ourselves, back in hardware, how to do that. There must be some operation, Boolean operation, which will let us selectively set or reset a bit and not affect any other bit. What would that logical operation be? Patricia, what do you think?
An and.
Yeah, it would be an and. And so in the case of, let's assume for a second that I have the very simple case of 8 bits, and below this, I just simply have something with zeros in it. If I want to take this bit and make it match this, or I should say, make the bit down here match this bit and mask off all the other bits, I want to take the first number and AND it with something that has a 1 in the position I want to pass through. So if both of these are a 1, this becomes a 1. If both of these were zeros, meaning I have a 0 here, if the bit I'm selecting is a 0, then a 0 passes through. So if I did that for the first position, and then I moved the top guy over 1, and the bottom guy I moved so that now the second bit is lined up with the second bit here, then I'd be able to make an exact copy of the number using exactly the same mask on each iteration of passing through. I could go 8 through 8 times. But I don't want to make an exact copy. I want this one to be in reverse order. So Robert, what do you suggest we would do?
So I actually wanted to raise an issue. when we ended it, it would erase all the previous data we had in there as well. So we probably don't actually want to end it in the first place.
Well, that might be true. And the
Um,
reason is because of the fact we have all of these as ones or zeros. So what do we want the and mask to look like? Or is it an and we actually want to use?
It's not.
What do we want to use?
We want to take just that 8th bit and OR it into our answer.
Okay, so that means we've got to somehow get rid of all the other bits, but somehow keep them for later.
Right.
Okay, so that sounds like a good working plan.
Well, except for the and's going to destroy all those bits, so we have to do
That's
something
right.
first.
That's right. So we're going to have to do something to maintain the remainder of the bits we have before we transfer the bit. So
There's a
we're
lot of
gonna mask.
landmines like that.
Oh yeah, we're going to mask the bits. But to mask the bits, we're going to be wiping out anything that's lined up with a 0 in our answer. But that's okay because we don't want our answer to include those. We only want to consider them when it's in this position. So we'll hold the ideas of ands and ors open for a second. But we'll remember the fact that we're only transferring a single bit, but we're trying to carry around 8 bits, which if we ever wipe them out, we have to be able to get them back. Now, to get things to happen in a reverse order, what can we do to both of these two numbers in order to reline up? For example, the first case, let's assume I did want to line him up with him. I've somehow already gotten him lined up. This guy needs to be lined up with him. This guy needs to be lined up with him. We do have a rotate instruction. Is there a way we could leverage that to somehow line those bits up? Robert, do you have another comment?
Oh, I have an answer.
And that would be?
You could rotate your top one to the left and rotate your bottom one to the right.
I like that. Now, we could be doing it on the other end as well. I mean, just because I'm doing it over here doesn't mean that's where it needs to be done. Could be done at any of the positions. But because we're making them happen in opposite directions, any rotations we do would have to go in opposite directions. Okay, very good thinking on that. Okay, so whatever mask we use needs to be specialized to allow the one bit we need to pass and to block all the others. But in the number we passed from, we have to somehow maintain all the bits that we didn't need. So as he points out, landmines aplenty here. So let's look at some code and track through a possible way we could have done this. Now, again, you may have done it differently, and there could be bugs. We won't worry about whether there are or not right now, because those would make excellent homework assignments. So let me actually just open up a DOS window here. I'm not going to give you a printed copy of this, so if you want a copy, you'll have to jot it down as we go. What is this? This is HWK1, I think I called it. Okay. Now, I overdid some, and I also used places where if we were writing optimized code, we wouldn't have done it this way. But this is, again, as a student should write it, not as it would be done professionally or by a compiler to generate it. So I'm going to store the number that I want to keep in a byte at 8,000. So I can run my program multiple times by changing that number. Okay, and the answer it comes up with here, 011011101. So let's look at that and the bottom number at the same time here. So if you guys read from the right, I'll read from the left. 10110110. So this number in reverse is that number. Okay, so what did we do to this number to make it happen? And I would have expected anybody in the class to have gotten this one right, because this is actually fairly, although there's landmines, it's a fairly simple problem. So we're going to pick up the number we want to reverse out of address 8000. We'll initialize the B register to 0 and the C register to 9. We're going to use 9 instead of 8 here so that we overshoot and back up a little bit. You'll see as we do it. Now, the first thing we're going to do is decrement C. Make that smaller by 1. If it ever hits 0, we're done. If we're done, we undo the accumulator's last rotate to the left by rotating it once to the right. We then move whatever's in the B register into the accumulator and undo its last rotate right by you doing a rotate to the left. I mean, right now the answer is in the A register, so we can output it and halt. So this basically undoes that 9th step, but it's cleaner that way. So what are we going to do here? Well, we're going to save a copy of what's in the accumulator. Yeah, I know we just loaded it, but next time around the loop, we won't. So whatever the condition of the accumulator is right now, we're going to save it at address 8000. We're going to mask off all the bits in the accumulator except for the leftmost bit. Remember we said we wanted to do that? Robert was pointing out how that worked. So now that we did that, we're going to load the accumulator from 8000. Now we're going to jump not 0 at this point to 1. We're going to jump a 0 to 0. Now don't worry about the fact we're doing something twice here. We store a number and what's in the accumulator and load over the top of it. Anybody want to take a shot at why we are doing that? Other than Robert. He and I could hold class all by ourselves, it seems. Patricia?
You're asking why you need to store and load the data because you need that data again for later. When you
Okay, but I store it here and I get it back right here. What did we ever do with the results of the AND?
It's in the accumulator, right?
Well, no, because we just wiped out the accumulator right here. There's a really good reason for doing it. Bazu?
I hit by mistake. I'm sorry.
Okay. Mikhail, why do you think we're doing that?
Is it so you don't erase the contents of?
Well, remember here, we save the entire thing. That's all the bits. Then we turn them all off except for the left one. Then we turn them all back on again.
Yeah, so then it would just be the same thing as before.
It would be the same before the store, yeah. But why did we do it? There's a good reason. Robert, why did we do it?
Actually, my initial impression is because we're doing it wrong.
That's a wrong answer. Let
Um,
me show you one thing here. Anybody remember this piece of paper? Remember load accumulator? What does it not do that jump if zero and jump if not zero are going to care about? I'll give you a hint. Robert?
it doesn't change the flag. Or
It doesn't. So does that mean and does? Well, look, the reason we did the and was specifically to test the one bit we need to, and it sets the flag, which we're now going to use. We want our data all back. Remember, we were worried about wiping it out, and that definitely wipes it out. We put it all back, but since this doesn't change the flags are now set for us to jump either to 1 or to 0 with this register re-intact. It's full again. Do you see that? Everybody see that?
so when it says none for the flags, that doesn't mean the flags are set back to 0, 0. That means it just doesn't touch the flags.
It doesn't touch the flag. That's
Oh.
correct.
So I had a fundamental misunderstanding there.
Okay. If it had actually changed them all back, it would have listed them all. Okay, so at this point, we know we had a 1 or we had a 0. If we have a 0, we don't have any work to do, so we'll jump to continue. But let's first of all do what 1 does. So 1 reloads, even though we have it here, it reloads back what's in the or what's at 8,000. It then takes, it moves, I'm sorry, it takes, I'm reading this backwards. It stores the good value at 8,000. We then wipe what's in A out with whatever's in B. And what was in B? Well, B had a 0 in it originally. So B is where we're going to be putting our answer. So if we're in the 1 branch, we're now going to OR into the accumulator, the leftmost bit. We're now going to take what's in the accumulator, put it back in B, and reload the accumulator with the correct value, and then jump to continue. Everybody understand that little chunk of code? Notice there's absolutely nothing fancy going on here. Now, once we get to continue, we're going to store the current value that's in the A register into our 8,000. We're going to move B into the accumulator and rotate it 1 position to the right. Then we're going to move it back to B. We're going to reload the value that should be in the accumulator, rotate it 1 position to the left, and then jump back and do it all again. And since we've seen all the code, that rotates the number, or that takes and copies the number in reverse order into another variable. Any questions? You notice most of this is because we only have 3 registers and we have to share one of them because the instructions use the accumulator an awful lot. If we had an A, B, C, and D register, we could probably get rid of a lot of those memory stores by putting things in D instead, making faster code. Remember, we're writing like students now, not like professionals. We won't be professionals till after the next assignment. Wait a minute. That's sorry. Scott, you have a comment?
Just a question. Is it possible in SAP 2 to implement this without reading and writing to memory?
We'd have to manage to keep them all in registers, all the values. And since we have two values that are being used to hold kind of the number we're manipulating and the result, and the third register is maintaining the number of times we have to do it, we could stretch it out so that we had 8 of the same things in a row. So we did each bit. But if we do it with a loop, we're probably going to have to give up one of the memory locations for that.
All right.
It's probably, there probably are other ways we could exclusive OR things together and carry 2 values in a single register, but that gets kind of tricky and we don't have a very powerful instruction set here. Robert, did you have a question?
Sure. So down at the bottom in the done loop, or the done label, I should say. So I noticed you rotate the accumulator right? The very first instruction there?
I rotate the value that was at
In
this
the
point
accumulator.
in the accumulator, right? Yeah.
Okay. And then the very next thing you do is you overwrite it with B. So that rotate the accumulator is unnecessary if this works.
Yeah.
So if
Okay.
that rotate AR, that
Like I say,
RAR,
we have to do an undo of the things above. A lot of these, like
Right.
these, the jumps
Mhm.
are unnecessary.
Well, but in that particular one is done is what's run at the very end, right?
Done is run. Where do we do run? Oh, it was up here. Yeah. When the loop is finished.
Okay. So if we go back down to that, you rotate the accumulator right,
That instruction is thrown away.
right, and
Okay.
then move B into A
The end.
is
and we
going to
rotate the
destroy that
accumulator.
rotation anyway.
Right. But
So-
because we moved B into A, we didn't save this anywhere.
Right, exactly. So it's unnecessary
There-
if
there-
this
there was-
works.
This is an optimization piece that I put back in and I didn't put the other register in. But
Oh,
in this
okay.
case, B, and so it's just like these jumps in a real professional environment, we would get rid of that because it doesn't do anything.
Okay.
This guy moves B into A and we had moved it one too many times. So we have to rotate it to the left because remember B is the guy where the answer is, but we need it in the accumulator in order to display it. So let's put another number out in here. Let's put 1, 2. I don't have an assembly run yet, do I? Okay, and the numbers we're expecting to find and anticipate ahead of time, what will the number be that we want to see here? So we write those bits out. We typed in 1, 2. So what we want to see in the lights are 0100, 1000. So let me grab the thing. So those two numbers match. So that's the reverse of the number we put in there. Let's try another one.
It didn't save, Professor.
I didn't save it. Why didn't it save it? Did I hit save as? I didn't want to do that. Hey, what do we expect this number to be? Write it down. 4, 8. You want to reverse that. Oops. And where's the thing? Here it is. That's what we got. Unfortunately, it matched. Okay. Anybody else have any questions or comments? It seems to work. Okay, now, let me be honest to you about this. That is a trap. How is that a trap, you might ask? My code frequently gets given away. Somebody will have copied this down and give it to a student who takes this either next semester or sometime in the future. When they turn it in, their code's going to look exactly like mine, including that one extra line. What does that tell me? Just keep that in mind, that occasionally things are instrumented a little bit because unfortunately, when we're not in the same classroom and I'm not watching you, there's a few people that'll take advantage of that sort of thing. And Robert unfortunately spotted that. And so he blew our cover on this one. We can't use it as a trap anymore.
Sorry, I won't do it again.
Oh, you did it one other time, or no, Scott. Scott did it one other time in the other class. So I'm not going to say what he managed to do, but he did a good job of it. Okay, so let's close this one down. But I can always tell the people that do that are my best students, so I'm usually glad to discover that. Let us take, and what's one next on my list here? Let's think about a problem here that might be a little interesting to you. I'm reaching over here trying to get a piece of paper and I can't quite reach it because I have the cat sitting on me right now and I don't like to give her a hard time. She leads a rough enough life. Is this the one I wanted? I believe it is. Okay, let's assume for a second that I was writing myself a piece of code. We know down here somewhere at the end of it there'll be, let me actually space this out properly. And we'll put a halt in front of it for now. Well, that's not it. What happened to my keyboard here? There we go. Okay, what I want to do is I want to print out that string. Who can tell me what the value inside that string is? Scott, what is it?
Capital A, B, C, D, and then like a null.
Yeah. Okay, so what it is, it's a null terminated string. meaning I don't know how long it is in advance, but I'm going to put a string here of at least 00, which means it's a null string, all the way up to, 240 characters or something. So I can put any length string here I want to. Now I want to print that out. So let's assume that I made a loop up here. Actually, I won't even make a loop. I'll do it so that I print it out. I want to load the accumulator with a byte of data that's located at 8,000. Then what I want to do is I want to check to see if it's equal to a 0. Because if it is, I'm done. So how can I check for 0? How can I check after I've loaded something in? Because we know the load doesn't do anything, right? Doesn't set the flag. Dante, what do you think?
Don't we just do jump not 0? Or jump 0 if we, depending on preference?
Okay, so we could do a jump if to start, and that way we would fall out. We'll put a jump there for now. We would jump to done. We would just fall out and continue. So after we loaded it, if we're done, we'll fall through, and yet if we're not done, we'll go back to start. But the problem we have right now is that load doesn't set any flags. So what am I going to do about that? Scott, what do you think?
We could do a or I with 0, 0.
Okay. Where would we do that?
It's got to be after we load the accumulator.
Okay, right after it? So you want me to do, whoops, an or I here of what value?
0, 0.
Like that?
Yeah.
Okay. And then we're going to do something in here. We have to be real careful, though, because the jump on not 0 is down here. What if we do some things in here that affect the flags? We'll lose the fact that this occurred. Do you see that?
Yep, that's a problem.
Uh-huh. Okay. Okay, so what sort of thing might we do? Well, we could guarantee somehow that the value is there and put it right before the jump not 0. We might have to redo the load. Oops. Might have to do something like that. And then we do our thing in here. let's assume that this was good enough. And we said out to 02, the character we just got. We're going to go to done. Done hits a halt, and we're completed with everything that's going to happen. So this loads what's at 8,000. Does that mean it's going to run forever and just print out 41? What's going to make me get down to the 0? What instruction? Robert?
Well, you would need to load 8,000, 1, 2, 3, 4 to get that 00.
Well, what instruction can I use to make this 8,000 change? This is the sheet you have to look at here, somewhere on this page. It's the clue.
You would increment 8,000. Or you would.
Well, incrementing 8,000 will make that a 42 instead of a 41. Right? There is no increment instruction.
Oh, yeah. So you just mean LDA hashtag 8004? Is that what you're looking for?
Well, yeah, but how would I? This is hardwired in the instruction. And I don't know how many bytes there are. There might be 240 characters down here. This is like an array, right?
Mm-hmm.
So how do we get from bucket 1 of the array to bucket 2? Ultimately, to get to bucket the end.
We would have to calculate how many bits we brought in and add it.
I don't know what that means. Scott, what do you think?
Rather than hard coding addresses, can we store them in a register? Have the LDA instruction get them out of the register?
You know what? You have just invented the SAP3. That's one of the features it has that this machine doesn't have. There are 3 things that are fundamentally architecturally poor about this machine. That's one of them. There's no such thing as a pointer in this language or in the architecture. The best we can do is we have addresses which are available to the store and load instruction, and that's the only place they can appear. And remember, this is hardwired in memory once you assemble it. You're going to go find the load of the accumulator opcode, then 00, then 80 in memory. So having no pointers is going to turn out to be an inconvenience to it. It's not insurmountable, though, because our machine is what's called a Princeton architecture or von Neumann architecture. It's not a Harvard architecture. In a Harvard architecture machine, instructions and data are in separate memory. In Princeton architecture, or the von Neumann architecture, which we're using, instructions and data are in the same memory. Does that give you any ideas? What do you think, Robert?
Could we, and I have no idea how we would actually accomplish that, but could we figure out where in the instructions in memory the instruction that is LDA 8000 and increment it?
Do you mean treat the instruction as though it were data?
Yes.
That's what von Neumann architecture allows us to do, isn't it?
Correct.
So if we were in a Harvard machine, we couldn't even think about doing that. But in here, we could simply treat the guy that does this as though it were data. And we could change the last byte every time around the loop. So when this load occurs the first time, it happens at 8,000. When it happens the second time, when it pulls the instruction in out of memory, this will no longer be 8,000, it'll be 8,001. And it'll keep doing that until it says 8,004, or whatever number this is. It'll pull a 0 out, which will tell the loop to end, and we'll be done. This, however, uncovers one of the other faults with the SAP2 that's fixed in the SAP3. Anybody see what that is? Well, what would happen if I located this initially at 8FFF? Dante?
I imagine we'd get some error or some sort as that data doesn't exist, or at least there's nothing in the data.
Well, we have data on this machine all the way up to FFFF, so it would give us the address 9000. Our data, of course, is not there. Our data would be at 8FFF and following bytes. But if we incremented this byte right here, and let's do that on a piece of paper. Didn't I have two of those open? When we had 8,000, we added a 1 to it, we got that. Added another 1 to it, we got that. We start at 8FFF, we add 1 to it, we get that, right? No. What's going to really happen is we're only adding to the rightmost byte. We're going to get 8F00, which is not where our data is at all. Our data would be at 8FFF, 9000, 9001. But because we're only updating this 1 byte, we would get a bad value. So you might say, well, why don't we take this byte and then add this, a 0 to this with the carry from this part? Just gave you a big clue. What does this machine not do when you add two numbers together? Robert?
It doesn't carry.
We don't have a carry flag. That's exactly right. So the first flaw, or the design workaround, is no pointers. Second one is no carry. We got one more to go, so I'll leave some dots there. But in general, this plan will work as long as we can find the spot to change. So if we were to treat this as data, what does that physically look like in memory? What would the 3 bytes be? What's the opcode for a load accumulator? Patricia?
Um, 3A.
And what is the next byte going to be? Mohammed?
Professor 3B.
What would the next byte be, Mikhail?
I was gonna say 3B2.
Scott?
Will be 00.
And finally, we have an 8,000. So if we could put this in data somewhere in memory, and we could point at that byte, as long as we make sure it's a 0 to start with, we got plenty of room for our 240 characters, right? We could actually put 256 there. And we'd be golden. So we need to write this as data using DBs and then call it. When we call it, it'll do its thing. Then we need to come back and update that byte before we use it again. So let's look at some code that does that. I'm going to clear this. Okay. We have a label down here called load. At load, we have 3 bytes, which is a load accumulator from address 8000. We can call this anytime we want to do that load, but we also put a label inside of it called M, which is for the byte we need to change. So we could do a store accumulator at any time at that address. We happen to know it's one more than wherever load is. And since we're using symbolic labels, the assembler will take care of figuring out where it is. And then we do this add and return. So let's follow through some code now and see what happens. I'm going to clear out register B and clear out register C. They both contain zeros now. B is going to be the offset register. Now I move B into the accumulator and I store it in the middle of the instruction. So I just put a set of zeros into the instruction. Now I call load. Well, I'm going to literally call that as though it was an instruction. We know it happens to be one. So it's going to load the accumulator from 8000 even. Add C and return. C is a 0, so it doesn't matter. Now, the call returns us back to here. We output the value. If at this point we have a 0 flag, we're done and we halt. Otherwise, we increment B. We call a function called wait. And then we jump back to loop and do it again. So when we do it again, we're going to use B into the accumulator, which now contains the number 1. Store that in the middle of the instruction. Call load. Load's going to now be 3A, but we put a 1 here, so it's 8001. Add the C and return. And we're going to do that until we get a 0. So this does exactly what it says it should do. This add down here is what we are using to make sure that the flags get set. Remember, C contains a 0. Load, this instruction right here, doesn't set the flags. So we just add a 0 to whatever's in the accumulator, and that'll give us the flags. Then we can return and continue on our way. Now look what wait does. Wait gets something out of the input register 1, checks to see if a character has been typed. If it hasn't, it waits some more. If any character is typed, we don't care what the character was. We simply acknowledge it and return. So that's going to let us get each character and look at it in turn. So let's look at this and see if we can make this one work. We have a 41. Any key. There's a 42. Any key. 43. Any key. 44. Any key will take us to, should find a 0. We should hit halt. This should stop scrolling. And we get the thing cleared. Let's change the size of the string and make sure it still works. What's capital D? Patricia?
44.
What's a lowercase o?
6F. Oh, sorry.
Oh yeah, Patricia already said it, but yeah, 6F.
I didn't. What was 6F?
6F, yeah, lowercase o.
6F, right? What's a G? Lowercase. Mohammed?
67.
GG. Put another one in. What's a Y? Lowercase y. Tamulin?
7-9.
Yeah, we'll see how close you guys got. $44. 6F. 6-7. 6-7. 7-9. Blank. Okay, well, assuming you got the ASCII right, we just did it. So this now can be of any length we choose it to be. And we could use random characters to test a longer number if we wanted to. I don't think we need to. The key things here are we turned our instruction into data and actually modified it in memory. We remembered to check and make sure that we had set the flags, and we drove those out to subroutines. Now, interestingly enough, on this machine, a subroutine works in a very peculiar way. So we're going along here executing instructions. We get a call. And down here we have address 4000. And well, make it look like the code you've been reading. And here we have a no op, and a return. So we execute this instruction. We execute this instruction. We go to next 4000, but on the way to going to 4000, we record the address of this next instruction. We put the return address at FFFE and FFFF. Now down here, once we're at 4000, we're going to do an instruction, and when we return, This restores the return address, which was stored here from that address, and we just continue after the call as though we didn't go anywhere. So these two addresses are used to contain the return address after a call, and a return will cause us to fetch them, put them in the program counter, and continue. Kind of think through that in your head and think if there might be any problems with that. Remember, I still have 3 dots hanging out over here. Let's write some code here while you're thinking about it. I'll just call it call.asm. Actually, we don't need to do that. Make it easy. And what I want to do is I want to put a subroutine here. Call it sub1. It'll have an instruction in it and a return. I'll put a second subroutine here. And it'll have a return. And up here, call sub1, call sub2. Let's just actually put our halt up there. We don't need it down here. Okay, so let's do an ASM. Call that ASM. Simulator. Call that hex. Now let's see what this did. Actually, let's make this even more easier to follow. I could be baiting you right now. Let's org this guy. 2000. So we'll know when we're in the subroutine. Org him to 4000. Okay. So we started at 0. We did our call, which did 2000 and then 2001, which brought us back to 3. We then called 4000, went to 4001, which brought us back to the halt. We actually should stick a no up there so we can see that we get back. Yeah, I'm going to make this a little more heavily notated here. Bio. Oops. There we go. Okay, so we got the start with our no op. We do our call, which is the CD, up to 2000. We do a no op. We then do the call. I'm sorry, what did we do in that? The return, which took us back to 4. We did a no op. We call at 5. Here's the things at 4000. We return back, and at 8, we have a no op right before the halt. Now, what do you think is going to happen if we take this put it here. Take your bets on what's going to be displayed over here. What do you think is going to happen, Robert?
So the problem we're going to run into is that we're trying to store a second thing to that data, and we're messing up where we're going to return. So we jump into sub 1, and we call sub 2, which puts us at org 2000. Or sorry. No, we go to sub 2, and then we return to what called us, which was sub 1, and we put org 4000, and then we try and return again, but the return is pointing at ourselves, so we're just going to endlessly loop to 4000.
That sounds pretty good to me. Let's see what's going to happen here. Okay.
Or, well, I guess 2000.
Or be 2000, but same idea. So what happens is exactly what he said. When we hit a call, it saves the return address. But if we hit a second call while we have a returned address, it's going to wipe it out. And we'll only have the return address of the second subroutine, which means every time we hit return, we'll keep coming back to the same place near 2000. And that's the numbers we're seeing here. So we've hit upon the third item. We don't have a way on this processor of doing nested calls. And that's a problem because it makes us have to write more complicated code than we would necessarily write. I sure would remember those 3 lines right there. No pointers, no carry, no nested calls. There's a fourth thing we're missing, but the SAP 3 doesn't fix it. We have to get to the 8085 before it gets fixed. And we'll talk about it being missing. Now, everything we have on this machine is so much better than the SAP 1, and we've been able to write a lot of things that a lot of people would have said were impossible. I've given that reverse the byte problem to some very seasoned assembly language programmers, or so they said, and they were unable to solve the problem quickly. I'm sure by the time they went home and thought about it for a while, they got it done. But nevertheless, the problems and the homework, if you'd spent 4 hours on it, you'd have had it. And programming assignments aren't necessarily, oh yeah, I get it, I'm just going to go home and write it in 15 minutes. You have to think about it, walk away from it, come back to it, get a plan of attack, and make yourself better at it. Don't be one of those guys that just kind of pretends to program and talks a big story but can't do it. Be the guy that can actually do it. Any other questions about this example? Scott, you have a question?
Yeah. Would it be possible to go back to the code that you had showed earlier, where we were transforming data into instructions into data? I only got the lower half of it.
Okay. I should have it here. What did I call that one?
I think it was.
Was that DRB 10?
Yeah, I think that was it.
It look like it?
Yep. Thank you.
Okay, which half do you need?
I needed the top half.
Okay. Okay, does anybody else have any questions or comments before we move ahead? Okay. One of the things I wanted to show you, Whoops. I swear I say don't save, and it does it anyway. He's here. This chip, the 74181, is pretty much the biggest and most featured TTL chip that it kind of still exists because we use it in schools a lot, but in practice you wouldn't use this anymore. You would instead use a PLD and write your own. But what this is this is a TTL arithmetic logic unit. If you recall in our processor for the SAP2, the box over here is an ALU. It's not an adder subtractor. It's the thing that we do all the additions and subtractions as well as logical operations in. The 74181 was a pretty useful chip. It had a pretty healthy insides. And we look at these tables here. This is just the Wikipedia, so it'd be easy for you to look up. There are different modes. If we want to treat the data so that a 0 means true, we use the first set of columns. If we want to treat it so we mean a high means true. In TTL, often you did the reverse, but we would do this in our thinking about it. Also, there's a bit called the M bit, which if set to high, means we're doing logic functions. And if set to low, means we're doing primarily arithmetic functions. There is a carry bit coming in, which if it's low, means there was no carry coming in. And there's a carry bit that could be high, meaning there was a carry bit coming in. Now, we have 8 bits, meaning we need 2 of these chips. But sitting side by side, they would have to have carry between the 2 nibbles, whereas they don't have a carry for the final flag. So this could have been used to represent the SAP2, but it would have not used all the features that this chip has. For example, if I set it for an arithmetic chip, I can do, well, where's a reasonable function that you know? I can just do simple addition, A plus B. And it will honor carry. It's either A plus B or A plus B plus 1, which we do in the left 4 bits if we were trying to emulate an 8-bit adder. We have A minus 1. That's the decrement function. Imagine if we look through here far enough, we'll find A plus 1, which would be the increment function. I don't see it off the top of my head right now, but it might be there. We do have some logic functions that leak into this part. And we also have some functions that we don't support, like A and not B minus 1. We don't support that as a logic function. But you can envision that into the ALU, besides the subtract line that we had on the SAP1, we probably have things that handle these force functions here. And again, this is a 4-bit chip, meaning that if we were to use it in practice, we'd have 2 of them. Between the 2, we'd have a carry flag that this guy, if he does an addition or a subtraction, would pass either carry or borrow by way of that line. 4 bits from each bidirectionally attached to the bus. We know that actually, did the ALU and ours attach to the bus? It might not. No, it does, because we have to write to the bus. We also would have 2 flags available coming out of these 2. There'd be something that says the left-hand bit is turned on here, so that's our 0 flag. And our 0 flag, meaning this and this both contain all zeros, could be a function of the output lines. meaning before they go to the tri-state buffers, they decode whether or not the 0 flag or the not 0 flag should be set. Remember, they're just the inverse of each other, so setting one or the other is easy to test. This is not a real flag. This is simply tested by an instruction as the absence of Z. The carry out of the second piece drops on the floor, though. It doesn't exist because we don't have a carry flag in the processor. So you might just be interested in looking at that, reading this article. It's a fairly interesting article. You can still buy these and hook them up if you're into breadboarding and doing things like that. This would be one to explore. Any questions about that? At the time the SAP2 was designed, it probably was the best ALU in town for doing this sort of thing cheaply with TTL logic. Okay, I have to do one thing here real quick. Okay, let me clean some of my windows up here for the minute. All right, is everybody through with this? Okay. That we probably need. That we don't at the moment. That we do. Okay. If you go to the lessons thing in Blackboard, you should find a file, drb99.txt. That's not it. Oh, I know where it is. I have to get it off the same place you do. So let me get it. Let me just verify that. Yeah, I'm going to have to get a copy of it as well. Okay, get that and stick it in a notepad or something. Actually, let me put it in this folder. I'm going to call it drb99.txt. And save it so I can get back to it if I lose it. Okay, did everybody get that file and get it loaded into a drb99.txt file? While strolling around the office of many secrets the other day, I stumbled across this program printed out. This program prints out the secret code for all secrets. And what we want to do is reverse engineer it. Now, this would be a wonderful question or exercise to do on an exam if we had one soon. So it might be one of those things you want to pay a lot of attention to how you go about it. And then we'll kind of structure what we're doing to see if we could make this happen again. So what our program apparently loads at address 0 on the SAP2 and consists of these bytes. My observation, I remember that a 76 is a halt. Because remember I said 76 trombones and everybody laughed really heartily? No, you didn't. But that's one of those lame dad jokes. So there's a halt at the end, a 76. So that's probably the whole program. So what we would do is we can't load it into an assembler because it's not assembly code. And not only that, when we first do this, we're going to pretend like we don't have an assembler. We're going to pretend like all we have is a loader. But we'll nevertheless have to turn it into assembly so we can by hand turn it into a hex file. So what we want to do is we first of all want to break this into the individual instructions that they represent. We can use this piece of paper to make that happen. For example, the first instruction is 3E, and we don't know how long it is, but we can find 3E on this chart and it'll tell us how long it's supposed to be. Who wants to do the first instruction? Patricia?
That's move immediate A7.
Okay, so this is a move immediate
A
A,
in a byte.
and what else does it need?
It goes through 70 states, no flag, and 2 bytes.
Well, it says move immediate. How long is that instruction? Should be on the right-hand end of the table.
2.
2. So we need 2 bytes. So far, we've used up the 3E and the 1-2. And it's a move immediate to the accumulator of the byte. So there'd be a 12 here. So those 2 are used up. We're sitting here. Who wants to do the next instruction? Hermal?
A move immediate of B of 34.
Okay, so I need to write here 06, 34, move immediate to B of the 34.
Yeah.
Okay. Now we're ready for 80. What's the next instruction going to be, Mohammed?
It will be add B.
Okay, so how many bytes is it?
That is 1.
There's an 80 here and it's an add B. Okay, what's the next? We're at this 47 now. Dante?
That's going to be move B, comma A. Move A into B.
Okay, and it's a 47 is the code. Move like this. In that order?
All the way around. Sorry, B into A.
Okay. Move A to B.
Move A to B.
Okay, we're ready for the 0E. Miguel, what's the 0E?
Move immediate C. And it would be.
We're going to move. What are we going to move? 5, 6? How many bytes am I going to take here?
2.
Okay, and they're going to be the OE and the 5, 6, right? Okay, now we're pointing at this 91.
Professor,
So what
you put O3 instead of OE.
Okay, 91. Basu?
That's a subtract C, 1 byte long.
What is it?
D.
What is it? SUB?
Subtract
Okay.
SUB C, and
that right?
it's a 1 byte long. Yes.
So this is a 91 over here.
Right.
Okay, we got a D3. Tamulin?
D3 is output 2 bytes.
Okay, so there's going to be the out, and the number looks like up there is an O2. So the thing here is going to have to take nibbles of D3, O2. Now we're pointing at the 76. We know 76 is a halt instruction. So if this starts at 4 zeros, we use 2 bytes. This is going to be at 2. Where is this one going to be? Let me move them over here. Where is the add going to be located, Hermal?
0003.
That would be right here on the 34.
Oh wait, it would be 004. There's 2
Okay.
bytes.
Okay, where's the 47 going to be? Mohammed?
0005.
How about the 00, or how about the 0E here? Nicholas?
It's going to be 0006.
Yeah, your microphone's very soft. Okay, how about the 91? Where is it going to be located? Robert?
0008.
And how about the D3? Andrew?
0009.
Okay, so this would be 9. What's the 76 going to be located at? Scott?
000B.
That's right, because we have A and B. And then the program is done at C. We would never get to C. So we now know what the assembly would be, but we don't have an assembler. We do have the code and the address where the code goes. So the next step we'd want to perform is we'd want to take and turn this into hex code. To do that, we need to take an example hex file. Let me just grab one here. And if you go check your notes, what you're going to find out is that we know what all of these fields are. We know that the last record is going to look like that no matter what. So I'm going to go ahead and put the last record in. Now we're going to have one of these other records per line. So let's take one. And we'll break it into parts here. It'll start with a colon. It'll have the number of bytes that are in the instruction. It'll have the address of the beginning of the instruction. It'll have a pair of zeros. It'll have the 2 bytes. And then finally, it'll have a checksum. And this guy follows that same pattern. Only thing is, because he's a typo 1, none of the other stuff makes any sense. So why don't you try to build, instead of DB01, this is going to be 3E12. That's our first instruction, add address 0. We know the second instruction is going to be at 02. So taking this whole thing and copying it again. It's going to be at 02, and we got to figure out what that is. So see if you can write out this X file. Go on down. Don't worry about the checksums for now. Just put 00 there for now, except for the last one, and leave it FF. So you need to supply some number of digits here. It says we're going to supply 2, but in this case, we'll only be supplying 1. That one's 1. This is 2. See if you can write this out. This would be great because you're going to do this again sometime really soon. You bunch of reverse engineers. I'm going to start doing mine. Somebody keep an eye on me. Make sure I type correctly. Somebody check me, make sure I type things correctly, make sure it matches yours. Okay, I'm going to close this one we don't need, the one we copied. And I'm going to open another notepad. And I'm going to call this one BRB, what was the name of our program, 99? 99.hex. And I'm going to copy all this stuff I just did into that file. And then I'm going to very dutifully here get rid of all the spaces. Remember to use this superpower I'm giving you of reverse engineering only for good. I've had to do this before when we've lost source code to a program and all you have is a printed copy. And printed copy of what was in memory. It's not broken down nicely like we've just done it. And I got to get rid of that blank line. Now, it looks like a hex file to me. I'm going to save it. Now, if I were to run this, meaning I simulate this, it should not work. Why would it not work? Patricia?
You didn't assemble it.
No, we don't need to if we created we just created this out of the reverse engineering it. We have an assembly file, but this is exactly what the assembly file would have generated, except for one thing. What's that, Robert?
Well, we didn't tell it where to start and where to end.
We don't have to. It always starts at 0, always stops at a halt. Scott, what do you think?
We didn't put in valid checksums.
Exactly. So if the guy that wrote the simulator code did a good job, then we would get an error. My guess is he didn't write an error because it's assuming this program is for adults. So what will happen is the program would just loop forever. But we should have, if I save that, be able to just simply simulate it. Should be able to say to sim drb99.x. And in our case, it looks like it's not caring that whether we gave it the things or not. However, let me see this for a second here. I think that might be a old version. Look at this. Make sure it's getting saved. It didn't. That was the problem. It didn't get saved in the right folder. What folder are we in here? We're on the OneDrive desktop. Let me see if I can read it over here better. Let's see if that happens. Nope, let me. I don't know. That's working too well for that to be just done. Well, that's the right one. Okay, well, I guess he wrote the code, so it didn't really care about the codes. Now the question would be, when we ran the simulator, did we get, I didn't look to see if we got our lights. Indeed, we did. So the secret code we've uncovered is 11110000. We reverse engineered into this. To make it correct, we should compute these. We'll do that in a second. Now, the other thing we have is we have the assembly code. So if we were to find the assembler, we could reconstruct it. So let's do that. Let's reconstruct the assembly code from this block of stuff. I'm going to make a copy of it. I'm going to hopefully in this folder, a notepad of drb99.asm. We'll paste this in. Now we need to turn it into an assembly program. What would you suggest the first thing I do is? Robert?
So you can get rid of these first 3 columns altogether.
Yep. Okay, so let's do that. We got to replace them with spaces, though. Scott, what should I do next?
I'm still thinking this one through.
Okay, what would make this look like an assembly program? What do I have to add? Let me give you a clue. First thing, we always have a start. The colon. What do we have down at this end?
Well, we'll have a assembler directive of end start.
Is there anything else we need to make that a program? Rob, what do you think?
I think we can load it up.
Okay, what we're going to do is I'm going to save it as a different name. I'm going to save it as drb98.asm. I'm also going to, over here, change this to all files as opposed to text documents. And I'm going to save it. Okay, drb98.asm. Now I should be able to say asm, drb98.asm. And it should have produced a hex file. So if I say notepad drb98.hex, this is what it produced. Let's see what we did by hand. Did I have that? Here it is. How do they look? Do they look like we reverse engineered exactly the same thing except for the checksums? And we generated all that without any computer assistance other than an editor. We took something that was a secret piece of programming code that somebody shouldn't have left laying around. It was just a printout of the memory. And we converted it into its basic program that told us what the secret code is. Of course, we're going to use that for good because the secret code is how do you get, candy out of the candy machine. But this is the case. Now, let's compute a couple of these hash codes. We can see what they are over here. Well, let's do this. If can everybody see the attendance list? Give me a green circle if you can see the attendance list. Participants. Okay, good. The first 3 of you do the first line's checksum. Second 3, third 3, fourth 3, fifth 3, sixth 3, seventh 3, eighth 3, ninth 3. I know we don't have 9 3s, but so the first 3 of you work out what the checksum is for that line. Remember, all you're going to do is you're going to add the 2 plus the 3e plus the 1, 2, get a number, take the 2's complement of it, and that's what should go here. We know it's going to be an AE. But go ahead and do that. So figure out where you are and do one of the lines in the thing. When you're done, we'll fill them in and make sure that they match. You should get the same answer we got over here. We just proved to yourself you can actually do that because on a test or something, you'd have to do it by yourself. And you'd have to get the checksum. This would be an incorrect answer because the checksums are wrong. Who got this guy? What number? Let's not look at this one for a second. Let's actually write down the number you got, and I hope you didn't just copy it off of here. One of your first three guys there? How about second three people? Did you get a checksum here? Dante, what'd you get?
Got the C2.
C2?
Yeah.
Okay. Who did this line? Did you get an answer? Make sure you know how to do the arithmetic. This line? Somebody get an answer yet? Next line, anybody do it? How about this guy? A couple of you that are done, go ahead and do the last three, because I'm sure we don't have enough people to cover it. And I don't know what some people, I think they're making coleslaw or something. They're not working on class material right now. Let's do the first one here. 0, 2 plus 3e plus 1, 2. So E, F, 0, 1, 2. What do I get? A 5, 2? 5, 2. This isn't right. What did I do? What did I add up wrong there? Or did I write this down wrong? Oh, I didn't put the 1 in. And this is an AE. AE, so we can say this is AE. Not a ZE. Third one. For practice, just do it even if it wasn't the one for you to do. The people didn't come up to the plate for this one at all. If it helps while you're working on it, separate it into its characters so you can see what adds to what. So this is 8O plus 4 plus 1. What's that, 8, 5? That'd be what, 0, 1, 1, 1, 1, 0, 1, 1. 7B. 7B. Okay, any questions about that? I'm not going to go through and finish it. If you finish it and reassemble it, get rid of the junk at the bottom again, save it, you simulate it, it should run. Sometimes the simulator loops forever if you have zeros up here. In our case, the version I'm running on Windows is different than the one I'm running on Mac, so it did differently. Robert, you have a question?
Yeah, so in the breakdown of the whole number, just let's do line 1, right? So we have O2, which is how many bytes the command itself is.
Oh, you want to go back to that? Yeah.
And then we have 0000, which is the memory's instruction, or where the instruction sits in memory.
Right, so these 4 are taken together as a group.
Right. And then the 00, what is that?
It tells what type of line it is. We only have 2 types. Those that have things to be loaded and those that don't.
Okay. So it'll always be 00 unless it's a 01.
At least with what we're doing, it'll always be 00. In
Okay.
bigger processors, it can have other values. And then this is the 2 bytes it said it's going to have. And then we always have a checksum at the end, which is simply sum up all the bytes and take the 2's complement and put it right there.
Could you break down line 5 real quick? Because I got a wrong number. That's why I didn't answer.
This guy. So for a checksum, you're going to add up 2 plus 6 plus 14 plus 86. So what do you get when you add that up?
That's where I got wrong. I wasn't adding the memory in. I was just adding the 2.
Oh, okay. Yeah, you got to do everything in the line. Anybody else have a question? I may have been calling these CRCs. If I do, they're not CRCs. They're actually just checksums. So if I've been using the wrong term, I apologize. A checksum is simply you compute it by adding things up. A CRC involves some rotation of the values, and we're not doing that here. Used for the same purpose, but we're not doing it. Mikhail, you have a question?
So I have the exact same thing as you, but it says error on syntax error on line 1 when I try to run it.
Assembly?
Yeah, when I do ASM, that's what it
Yeah.
says.
I don't even know where my copy is right now. That guy? I think that's the guy. His looks exactly like mine.
Yeah, let me just do it again.
Okay. While he's looking at that, talk to me after class if you can't get it to work. There'll be a typo somewhere, either in the code or there's any number of things could be going wrong with that. But usually it points to the correct line, at least in my experience, it has. Let me close some windows here.
Professor, if I might, I have a question for Mikkel.
Sure.
Mikkel, are you running ASM on the ASM file, or are you running it on the hex file?
Never mind, because I worded the file wrong. Never mind.
Okay, that's fine. That's good. Yeah, I've done that before with the point at the wrong file. It does think it's an error, that's for sure. Okay, you'll need this page up for a second, and you'll need your diagram of the processor up. Don't know if I can get them both on the screen at the same time. Okay, what I want to do is I wanted to take and look at one of the instructions and see if we can figure out the t-states. This would be a great thing to see if you understood the architecture pretty well. Let's start with something really simple, like a move B to A. It moves from right to left. In our case right here, it says it's going to take 4 t-states. So what signals do we expect to be present in the 4 t-states? Think about it for a second, looking at your picture. And then let's determine what should be on the bus and what should be available control signal wise at each step of the way. Okay, who has an idea of what should be asserted during T1? Scott, what would you say?
Kind of a guess. We'll enable program counter and load the MAR.
Yep. Okay, that's very reasonable. We've taken the current instruction, which we don't know what it is yet, put it on the bus, put it in the MAR, so that now we can take it out of the RAM and move it somewhere during T2. So we've got to get the data, which is in memory, data which is in memory on the bus. There is no connection between memory and the bus. So what do we have to do? What signals are going to be during T2? Okay, I'll help you with this one. Obviously, the data register is going to write to the bus. So we're going to have to enable the data register. In order to get this guy to put his data where this guy can see it, two things have to be asserted on this two signals. It needs to have write asserted and chip enable. So it's not writing to the bus, instead it's writing into the data register, who will write its contents on the bus if you say enable the data register. During T2, we also can bump the program counter. So T1 and T2 are the fetch cycles for this particular instruction. Now, what else do we have left to do? Scott, what do you think?
Load the instruction register.
Okay, so where is that going to happen?
That'll be a, we would assert a load signal on IR.
But where do we do that? Which T state?
It's, I was guessing it's part of T2.
It is. The instruction register. So now what do we have left to do? The instruction register knows what the instruction is, so it's generating all the right control signals for a move instruction, specifically the move B to A instruction. So what signals are likely turned on right now? Robert?
You're enable B and load A.
And what's going to happen during the next T state? Your hand still up, Robert, or is that old hand?
Yeah, I think I got this one. I'm not entirely sure, but I would think that we would load the location of the next instruction.
Well, we got that right here when we had bumped up the program counter.
Oh, okay. Then I'm not quite sure.
Okay. Anybody else have a idea? Well, we could do it in 3 T states like this. This did everything we needed to do, correct? More than likely, though, it would have been done this way. And only one of those. Because generally memory is a little slower than the rest of the devices. Very often they will give you extra time for the data to be written from memory into the register that's going to present it to the bus. Now, actually, we would get rid of enable D here. So what we would do is we would say to the chip, right, chip is enabled, and we would hold that an extra state while we make this count. This guy's on the wrong line. And then the state where we'd actually move it from the D register would be here. We'd still have to hold these 2 signals because we'd still want to broadcast the data into the data register. We could write it in such a way that this bus latched on a clock, but we don't need to. We could use a simple mechanism like this. Now, this is one of many debatable items on how, as long as the signals ultimately get the data where it needs to go, we're in pretty good shape. One of the things we have to think about, though, with this is not all instructions are 1 cycle long. Because if I took a move immediate, for example, once I get the instruction into the instruction register, I still have to get the second byte out of the instruction. Yes, it's immediate data, but it's going to wind up in this temp register over here. But I would have to do that. So a move immediate is going to take more T states. What is it, 7 on this machine, probably? Yeah. So let's think about that for just a second. Move immediate. And we'll do the one that goes into the accumulator, and we'll just put a 0, 0 in there. I take 7 T states. And it's a 2-byte instruction. So we know in T1, we'll enable the program counter. We'll load the memory address register. In T2, we're going to enable memory, bump the program counter, enable Chip enable and load the instruction register. In T4, we know what the where it is. However, we don't have the data yet, so we have to get it. We've counted, so we're pointing at it. So to get it, we once again have to enable the program counter, load the memory address register so that we can get the byte out. And if we do that, we'll need our write, chip enable, and CP combo. And we'll need the EDWCE, but not load the accumulator this time. Instead, this time we'll load the temp register. Do lowercase t. And then in T7, which is where the move has to occur, we'll enable T, we'll load the accumulator. 7 T states. Sometimes we will break these T states into what we call M states. In this case, this set and the next, in this case, 4, but sometimes 3. Actually, it'd probably be broken like this. We would have M1 and M2 and M3. Might really just be M1 and M2. I don't know in this processor how they designed it. Don't remember. So this is how you can sit and develop up and see where these numbers came from. The 10s, these 10s and 7s, you might have to work at it to get the exact number you need. But if you think about it a while and what the machine has to do, and with your experience with the SAP1, you should be able to get this to happen. Okay, let's talk homework for a second. Let me get the thing up on the screen here. Okay, let me think if I can remember what the name of this thing is. Okay. You're going to write a program that, it's over here running away, that will let you type 2 decimal numbers. So the numbers you type, no error checking, we're not trying to make a production version, can go from 00 up to 99. You can only type numbers that are decimal. So let's say I type the number 35. When I type the 3, the top 4 bits will show a 3. When I type a 5, the 5 will appear here. So I have the number 35. Now, when I click any button, I'll click the 0 here. If I click any button, it'll convert it to hex. 32 plus 3 is 35. Let's do that again. I type 99. And there goes the 9 in the top 4 bits, 9 in the bottom. So this is decimal, 99, 4-bit, 99. Now, when I click another key, it'll convert it to hex and display the answer, which will be, what, 63. 63. I want you to write a program that will do exactly what I just showed you. We'll turn it in at the start of class like we always do. And your test next week will be somewhat dependent on how well you do on this homework assignment. If you don't get the homework assignment right, I'm going to test you much, much more thoroughly than if you get the homework assignment done. No cheating, no copying. I'll know that in a heartbeat. So make sure that you do it. Mikhail?
Wait, sorry. What is the homework assignment to do?
I'm going to show it to you again. You should have paid attention, but I'll show it to you again. Okay, it's going to be done and turned in at the start of class on Wednesday this week. And what your program needs to do is when you simulate it and this window comes up, it wants you to type a 2-digit decimal number. So let's say I type a 50, there's a 5, 3, there's a 3. So 5, 3, that's the decimal number I typed. When I click another key, I want you to convert it to hex. So 53 is a 3. There's a 3 in hex. There's a 5 in hex, a 3, 5. So it's 48 plus 5. Did that explain to you what the program needs to do?
Yeah, I got it now.
Okay, anybody else need to see it run again or need more direction on where it is? Very simple. But you want to make sure you do it, you get it done, and that when you turn it in, you can explain it. Don't be explaining somebody else's because you won't understand it when I ask you. And there'll be a question or two on the exam which involve this program. And if you haven't turned in one that's valid and that you wrote, then you're going to have a lot more trouble with it when you get to the exam. Anybody have any questions? I hope you all had as exciting a night as I do. No longer do I have to go to a party and tell them, that I can see their sign and they're a Virgo. Instead, I can calculate their checksum instead and really be popular. So I'll see you guys on Wednesday night, and you get working on this as soon as we get finished class here so you can get it done, and then you won't have to worry about it until then. Have a nice night.